Every glossy vision of Mars you have ever seen, the gleaming domes, the sunset picnics under a butterscotch sky, the confident astronauts striding across red dunes, is hiding a truth that almost nobody talks about, and it is this. Mars is not just difficult to live on. It is actively, quietly, relentlessly trying to kill you, in ways far stranger and more insidious than a single dramatic disaster. And tonight we are going to talk about the real dangers, the ones that do not make it into the recruitment posters. We have spent decades dreaming about Mars as humanity's next home, and for good reason. It is the most habitable planet in our solar system after Earth. It has a similar day length, evidence of ancient water, and a surface area roughly equal to all the dry land on our own planet combined. But habitable is a relative term, and when you actually break down what the human body and the human mind require to survive long-term, Mars reveals itself as one of the most hostile environments we have ever seriously proposed moving into. Not hostile in the way of erupting volcanoes or monstrous storms ripping buildings apart, but hostile in a slower, more clinical way, the kind of hostility that shows up in blood work, in bone scans, in psychological evaluations, and in the failure logs of life support systems millions of miles from help. This is the story of what living on Mars would actually cost the human body, the human mind, and the fragile technology standing between a colonist and the vacuum of space. Let's start with the danger most people assume is the biggest, and it is radiation, but probably not in the way you are picturing it. Earth has two enormous natural shields protecting every living thing on its surface. The first is a thick atmosphere that absorbs and scatters incoming radiation before it ever reaches the ground. The second is a global magnetic field, generated by the churning molten iron core beneath our feet, which deflects charged particles streaming from the sun and deep space around our planet like an invisible force field. Mars has neither of these in any meaningful capacity. Its atmosphere is less than 1% as dense as Earth's, and its magnetic field died out billions of years ago when its core cooled and stopped generating a strong dynamo effect. Without these shields, the surface of Mars is bathed in a constant drizzle of cosmic radiation, and during solar storms, occasional spikes of dangerous high-energy particles blasted out from the sun. This is not a hypothetical concern measured only in theory. Instruments aboard the Curiosity rover have been quietly recording radiation levels on the Martian surface since it landed, and the data paints a sobering picture. A colonist living on Mars for a single Earth year would absorb a radiation dose many times higher than what is considered safe for radiation workers here on Earth over that same period. Long-term exposure at these levels is linked to significantly elevated cancer risk, potential damage to the central nervous system, cardiovascular problems, and cataracts. Unlike a single dramatic radiation event you might see in a disaster film, this is a slow accumulating exposure, the kind that does not announce itself with any symptom for years, quietly raising the odds of serious illness the longer a person stays. Solving this problem is not simply a matter of wearing a heavier spacesuit outside. The real solution being explored involves burying habitats under several meters of Martian soil, known as regolith, or carving out living spaces inside lava tubes, natural underground tunnels formed by ancient volcanic activity, which would provide substantial natural shielding. In other words, one of the biggest dangers of living on Mars is that meaningful long-term survival may require living underground, permanently, away from sunlight, away from open sky, in a way that fundamentally changes what daily life on Mars would actually look like. Which brings us to a danger that receives far less attention than radiation, but may prove just as devastating over time, and that is gravity, or rather, the lack of enough of it. Mars has roughly 38% of Earth's gravity. Step onto its surface and you would feel noticeably lighter, able to leap higher and carry more relative to your own body weight. It sounds almost fun in theory, but the human body evolved over millions of years under a very specific gravitational load, and removing most of that load creates serious biological consequences. We already have decades of data from astronauts living in microgravity aboard space stations, and the results are consistent and concerning. Bones lose density at a rate of roughly 1 to 1.5% per month in zero gravity, concentrated heavily in weight-bearing bones like the hips and spine. Muscles, especially those responsible for posture and movement against gravity, atrophy rapidly without intervention. The cardiovascular system, no longer needing to pump blood as forcefully against gravity, weakens over time. Mars' gravity is not zero, so these effects would likely be less extreme than what astronauts experience on long space station missions. But scientists do not yet know exactly how much protection 38% gravity actually provides, because no human being has ever lived under partial gravity for an extended period. This is one of the great unknowns of Martian colonization. A generation of colonists could potentially develop chronic bone density loss, muscle weakness, and cardiovascular deconditioning that makes eventual return to Earth's full gravity difficult or even dangerous. And children born and raised on Mars might develop bodies fundamentally adapted to lower gravity in ways we cannot fully predict: skeletal structures, muscle distribution, even cardiovascular systems shaped by a world with less than half the gravitational pull their ancestors evolved under. Beyond radiation and gravity lies a danger that is almost mundane by comparison, yet arguably one of the most immediate threats to survival, and that is the simple, brutal chemistry of the Martian atmosphere and soil. The air on Mars is roughly 96% carbon dioxide, with almost no oxygen, and atmospheric pressure so low that unprotected human blood would begin to boil at body temperature, a gruesome phenomenon known as ebullism. Stepping outside without a full pressurized suit is not survivable for more than a matter of seconds. Every single excursion outside a Martian habitat becomes a fully sealed life support dependent event, no different in principle from a spacewalk in orbit, except colonists would need to do this constantly for construction, maintenance, exploration, and basic operations, turning what would be a rare, carefully planned event on a space station into routine daily life. Then there is the soil itself, which contains a class of chemical compounds called perchlorates, salts that are toxic to the human thyroid and nervous system in sufficient quantities. Martian regolith across large portions of the planet's surface contains measurable concentrations of these compounds, discovered by the Phoenix lander and later confirmed by Curiosity. This means the very dust that would inevitably work its way into habitats, cling to spacesuits, and settle on equipment is not simply gritty and abrasive. It is mildly toxic, and any long-term Mars settlement would need rigorous decontamination protocols to prevent this dust from being tracked inside living quarters, breathed in, or introduced into food and water systems. Combine this with the sharp, jagged microscopic texture of Martian dust, formed without the weathering effect of flowing water and wind erosion patterns we have on Earth, and you get a substance that is not just chemically irritating, but potentially damaging to lung tissue if inhaled over long periods, not unlike the respiratory illnesses experienced by miners and industrial workers exposed to certain fine particulates here on Earth. Now let's talk about the weather, because Martian dust storms have a reputation, largely thanks to popular science fiction, as violent, howling, structure-toppling events, and the reality is both less and more concerning than that portrayal. Due to the thin atmosphere, Martian winds, even during major storms, would not hit a standing human with anywhere near the destructive force depicted in some films. The atmosphere is simply too thin to carry that kind of kinetic punch. However, global dust storms on Mars are very real, and in 2018, one such storm grew so massive it enveloped the entire planet for months, dramatically reducing sunlight reaching the surface and ultimately contributing to the end of the Opportunity rover's mission after it could no longer recharge its solar panels. For any Mars colony relying even partially on solar power, a global dust storm represents a genuine existential threat, a months-long reduction in available energy at precisely the moment when heating, oxygen generation, water recycling, and every other critical life support function needs uninterrupted power. This is one of the strongest arguments colonization planners make for relying primarily on nuclear power sources rather than solar arrays. Because a colony that loses power for an extended period during a dust storm is not facing inconvenience, it is facing a genuine life-threatening systems failure. Let's talk about temperature, because Mars is cold in a way that is difficult to fully appreciate until you look at the numbers. Average surface temperature hovers around -60 degrees Celsius, and while equatorial regions can occasionally reach a relatively pleasant 20 degrees Celsius during a summer afternoon, nighttime temperatures can plunge to -125 degrees Celsius near the poles. This constant, extreme cold means every habitat, every vehicle, every piece of exposed equipment must be engineered to handle brutal thermal cycling day after day, year after year, and any failure in heating systems during a Martian night could turn a livable habitat into a lethal freezer within hours. All of this technical and biological danger exists within perhaps the most underappreciated hazard of all, one that has nothing to do with radiation, gravity, or temperature, and everything to do with the human mind. Isolation psychology is an enormous concern for any long-duration Mars mission, and researchers have studied this extensively through simulated missions here on Earth, including facilities in Hawaii and Russia designed to mimic the confinement and isolation of a Mars journey. The Earth-to-Mars communication delay alone creates a profound psychological burden. Depending on the relative positions of the two planets, a message can take anywhere from about 3 to 22 minutes to travel one way, meaning real-time conversation with anyone on Earth becomes completely impossible. Imagine a genuine medical emergency, a family crisis back home, or simply a moment of overwhelming loneliness, and knowing that even the fastest possible message to another human being off this planet will take many minutes to arrive, followed by an equally long wait for any response. Every conversation with Earth becomes a delayed, deliberate exchange, nothing like the immediate connection we take for granted through phone calls and video chats today. Then there is the sheer monotony and confinement of the environment itself. Mars colonists would likely spend the vast majority of their time inside pressurized, artificially lit habitats, with limited private space, a small and unchanging social group, no ability to simply go outside for fresh air without an elaborate suiting up procedure, and a landscape outside that, however scientifically fascinating, remains a rust-colored, largely unchanging desert stretching to the horizon in every direction. Studies of isolated environments here on Earth, including Antarctic research stations, submarine crews, and simulated Mars habitat missions, consistently show increased rates of depression, anxiety, interpersonal conflict, and a phenomenon researchers call the third quarter effect, a documented dip in morale and psychological well-being that tends to occur roughly midway through long isolation missions. After initial novelty fades but before the relief of an approaching return date provides motivation. On a Mars mission, that return date might be years away, and initial colonists may face the psychological reality that they are not simply on an extended mission, but permanently relocating, never to feel Earth's gravity, breathe unfiltered air, or feel real rain on their skin again. This leads to a danger that sounds almost philosophical, but has extremely practical consequences: the total and complete dependence on technology for every single biological need. On Earth, if your air conditioning breaks, you get uncomfortable. If your water filtration system fails, you can still breathe. If your food supply is disrupted, you have days or weeks before it becomes critical. On Mars, oxygen generation systems, water recycling systems, Temperature regulation and food production are not conveniences layered on top of a naturally habitable environment. They are the only things standing between colonists and immediate death. A significant failure in life support systems is not an inconvenience to be fixed at your leisure. It is potentially a countdown measured in hours. And unlike a problem on the International Space Station, where emergency supplies or even evacuation could theoretically arrive within days, any serious equipment failure on Mars must be solved using only the tools, spare parts, and expertise physically present at the colony. Because meaningful resupply from Earth takes months to arrive even under ideal orbital alignment, and there is no possibility of rapid evacuation back to Earth under any circumstances. This is where redundancy becomes not just good engineering practice, but a matter of survival, and it is also where one of the least discussed dangers of Mars colonization becomes apparent: the psychological weight of living inside a completely artificial, completely fragile life support bubble, permanently aware that the air around you is only breathable because of machines that could, in theory, fail. Long-term studies of submarine crews and space station astronauts show that humans can adapt remarkably well to this kind of existence, but it requires careful selection of personnel, extensive training, and habitat design specifically intended to reduce the psychological burden of constant technological dependence. Things like access to natural light simulation, private quarters, meaningful work, and strong social support structures within the crew. Let's also talk about medical care, because this is a danger that becomes far more serious the moment you consider realistic scenarios rather than best-case ones. A broken bone, an appendicitis, a serious infection, a complication during childbirth. All of these are manageable, even routine, in a well-equipped hospital on Earth. On Mars, especially during the early decades of colonization, medical facilities would necessarily be limited, staffed by a small number of cross-trained personnel rather than specialized surgeons, and completely cut off from the possibility of emergency evacuation to a better-equipped facility. A medical emergency that would be a same-day resolved issue on Earth could become a genuine crisis on Mars, particularly for conditions requiring specialized surgical intervention, blood transfusions matched to specific types, or equipment simply too large or specialized to include in an early colony's limited medical bay. Researchers have specifically studied the risks of pregnancy and childbirth in reduced gravity and high radiation environments. And the honest answer is we do not yet fully understand how these conditions would affect fetal development. And there are serious open questions about whether early colonization phases should even attempt reproduction until far more data exists. There is also a subtler biological danger worth discussing, related to the human immune system and the broader ecosystem of microorganisms that live on and inside every human body. Our immune systems evolved over hundreds of thousands of years in constant interaction with Earth's rich, diverse microbial environment, exposure to soil, other people, animals, plants, and an enormous variety of bacteria and other microorganisms that help train and regulate immune function. A sealed Martian habitat, by necessity kept extremely clean and controlled to prevent contamination of both the colony and the Martian environment itself, would represent a radically reduced microbial environment compared to Earth. Some researchers have raised concerns that long-term life in such a sterile, controlled environment could lead to immune system dysregulation, similar to patterns already observed in extremely clean modern indoor environments here on Earth, potentially increasing susceptibility to allergies, autoimmune conditions, or reduced resilience against infections that would normally be handled easily. And then there is a danger that sounds almost too strange to be real, but is taken extremely seriously by planetary scientists: the risk of biological contamination in both directions. Any human presence on Mars carries a real risk of introducing Earth microorganisms to the Martian environment, potentially contaminating any native Martian microbial life that might exist, particularly in subsurface water reservoirs, and permanently compromising our ability to study whether Mars ever independently developed life of its own. This is not merely an environmental preservation concern. Planetary protection protocols exist specifically to prevent this kind of contamination, because once introduced, Earth microbes could potentially outcompete or destroy fragile native Martian life before we ever have the chance to properly study it. Conversely, there are also serious, ongoing scientific discussions about whether it is even possible to fully guarantee that samples, equipment, or colonists returning from Mars could not inadvertently bring back Martian microorganisms that our own immune systems and ecosystem have never encountered before, an appropriately cautious concern that has shaped strict quarantine and decontamination protocols for any future sample return missions. Let's also address fire, an often overlooked danger in a sealed, oxygen-controlled environment. In a pressurized Martian habitat, the atmosphere would likely be carefully balanced, potentially with elevated oxygen concentrations compared to Earth's sea-level atmosphere to reduce overall cabin pressure requirements while still providing breathable air. Elevated oxygen environments dramatically increase fire risk. Materials that barely smolder in normal air can burn rapidly and intensely in an oxygen-enriched atmosphere, a lesson tragically learned during the Apollo program here on Earth. Fire suppression in a sealed habitat becomes an enormously complex engineering challenge, because you cannot simply evacuate to fresh air outside, and depressurizing a habitat to starve a fire of oxygen risks the lives of everyone inside just as much as the fire itself. Even something as seemingly minor as static electricity becomes a genuine engineering concern on Mars. The extremely dry, fine dust that covers the planet's surface, combined with the thin atmosphere, creates conditions where static charge can build up significantly on equipment, vehicles, and spacesuits, potentially damaging sensitive electronics, or, in an oxygen-rich environment, even creating spark ignition risks near fuel or life support systems. This is exactly the kind of danger that never makes it into inspirational Mars colonization artwork, yet becomes a serious daily engineering consideration for anyone actually designing equipment meant to survive and operate reliably on the Martian surface for years at a time. Now let's zoom out and talk about resources, because ultimately every danger we have discussed connects back to one central challenge. Mars offers no natural infrastructure whatsoever to support human life, and every single resource a colony needs, breathable air, drinkable water, edible food, usable energy, construction materials, and replacement parts, must either be brought from Earth at enormous cost or manufactured on site using technology that, in many cases, does not yet exist at the scale required for permanent settlement. Techniques like extracting water from subsurface ice deposits, generating oxygen from the Martian atmosphere through electrolysis, and using 3D printing with local regolith to construct radiation-shielded habitats are all promising areas of active research. And missions like the Mars Oxygen In Situ Resource Utilization Experiment aboard the Perseverance rover have already successfully demonstrated small-scale oxygen production directly from the Martian atmosphere. But demonstrating a technology at experimental scale and reliably scaling it up to support a genuinely self-sufficient colony of hundreds or thousands of people are two very different challenges, separated by decades of engineering development, testing, and inevitable failures along the way. This is perhaps the most important and least discussed danger of all, not a single dramatic threat, but the compounding, interconnected nature of every risk we have covered tonight. Radiation exposure increases cancer risk over years. Reduced gravity weakens bones and muscles over months. Psychological isolation erodes mental health over the course of a mission. Equipment dependence means any single point of failure in oxygen, water, or temperature control systems can become fatal within hours. Toxic dust threatens respiratory health with long-term exposure. Medical emergencies that would be routine on Earth become potentially catastrophic on Mars. None of these dangers exist in isolation. They interact, compound, and place enormous pressure on both the engineering systems and the human beings tasked with keeping a fragile artificial life support bubble functioning permanently, on a planet that offers no natural forgiveness for mistakes. None of this means Mars colonization is impossible or that it should not be pursued. Every danger discussed tonight is actively being studied, modeled, and engineered around by some of the most brilliant scientists and engineers currently working at space agencies and private companies alike. Understanding these dangers honestly is not pessimism. It is the exact process that will eventually make sustainable Mars settlement possible. Because every problem correctly identified today is a problem that can be solved with enough time, testing, and innovation before the first permanent colonists ever step onto that rust-colored surface. But it does mean that the popular vision of Mars living, gleaming domes and casual sunset walks, deserves a serious reality check. Because moving to Mars will not be like moving to a new country. It will be like permanently moving into a hostile, unforgiving vacuum with a thin, toxic atmosphere, extreme cold, constant radiation, weakened gravity, and total dependence on technology that must never be allowed to fail. All while separated from the entire rest of humanity by a communication delay that turns even a simple phone call into a patient, deliberate exchange stretched across the emptiness of interplanetary space. If humanity is serious about becoming a multiplanetary species, and there are compelling reasons to believe we should be, then respecting these dangers rather than glossing over them is exactly what will make the difference between a tragic historical footnote and a genuinely sustainable new branch of human civilization, permanently rooted on another world. Thank you for spending this time with us exploring the real, often overlooked dangers of living on Mars. If this deep dive into the true challenges of Martian colonization gave you a new perspective, consider subscribing for more honest explorations of space science and the future of human exploration. And let us know in the comments which of these dangers surprised you the most.